let's focus actually on simple shapes. And simple shapes ultimately will be rectangles, triangles, and such things. But for now, I would like to focus on this potato chip here. It's actually not a potato. It's important to understand that we're talking about an area. And so the area is really a potato chip. And you see that this area has ultimately many of these DAs, so tiny area elements, and each area element has a centroid location in the middle of this area element, and that has a distance to the origin of the coordinate system. So you see the distance here is given with y and with x, and if I now want to talk about the moment of inertia, let's now start deriving the formulas. So I'm going to call that Ix, and that means the moment of inertia is the I, MOI, and the x means about the x-axis. And that is very important to me. In fact, I will highlight that for you right now. This about here is very important. I need you to understand that we're talking about the moment of inertia about the x-axis. And it's defined as follows. If you really use integration math here, then you use the area integration of y squared dA. And let's talk about that for a second. So where does this y come from? It's kind of confusing, right? Because we're talking about Ix, and then we have a y here in the formula. But if you think about it, it's the moment of inertia about the x-axis. So that means about this axis. And if you think of this area element, dA, rotating about this x-axis, then the lever arm is the y direction. So I want you to imagine this potato chip or the area element to rotate about this axis. So right now it's coming towards you, towards you, towards you, towards you, towards you, and now it's moving away, 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 and then it moves away, 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 and then it comes towards you, towards you, towards you, and it comes towards you, towards you, towards you, and so on. So that is how the potato chip rotates about the x-axis, and for that to happen, you need to have the distance y. And it's very confusing for beginners to have the moment of inertia about the x-axis and then see a y in this equation. But you can probably now, with the help of this picture, understand where that is coming from. Another very important thing is that we have the squared component here. So the squared component is very important because students all the time forget this. And I have made bets with my students in the past, jokingly, that if nobody forgets to square this, then everybody gets an A on the final exam. And you know, I never had to do it. I probably have taught thousands of students and made the bet with thousands of students that if nobody in the class forgets to square this component, then everybody gets an A. But apparently the students didn't like that. They didn't want that A because at least 5 out of 50 students keep forgetting to square that. But it's a very important part, and you may ask yourself, why is this? Why do I have to square this? And it has something to do with the rotation about the x-axis, and it's physically very complicated to explain. However, I think you all have experienced this in one way or the other. So let me take you down memory lane. When you were playing in the backyard with a bucket of water, and you put the bucket of water on your hand, and you rotated it above your head, and you were surprised that the water didn't fall out. And this falling out of water has nothing to do with the moment of inertia, but the force that you felt when you rotated the bucket in your arm, you actually had something to do with this component here. So think about that. If you extended your arm longer and longer, if you made this very long, in fact, if you maybe even add a string to that bucket and you keep rotating it, you will very quickly realize that you cannot hold on to the bucket anymore. And why is that? Because you're actually experiencing the square component here. So the square component becomes much more intense if y gets larger. And again, you can experience this when you rotate the bucket, because the further away the bucket gets from your shoulder, if you will, take the shoulder as your rotation point, then this will actually increase and increase. And remember that before, when we talked about the moment of inertia, when we talked about the centroid location, right? I'll write that formula again. Centroid location was the sum of x tilde I, or actually let's talk about y tilde ai, which then would make this here also y. So let's fix that. And then sum ai. And remember that this part here in the brackets was the first area moment about the x-axis, right? So this is about x-axis for the very same reason as I explained here on this page. But now notice that I actually have a second area moment, and this is where the square comes in. And so this here is a second area moment, and this is the definition for that. So, and what is it? It's the lever arm squared times the area, which also tells us something very important about this formula, and that is that the units, and I'll let you guess for a second what the unit will be. So the unit, of course, will be lengths times lengths times lengths times lengths. So we have a very strange unit here, which is actually lengths to the power of 4. And so this must always be true. It must always be lengths to the power of 4 because you have a lever arm that is squared times an area. And that's how we quantify the moment of inertia. So the moment of inertia usually ends up with meter to the power of 4 or inch to the power of 4 or feet to the power of 4, whichever one you want. So that has always been true. It's very difficult for a beginner to get used to these dimensions, but maybe you can memorize for now that it needs to be to the power of 4 because you have a lever arm that is squared and an area that is squared. All right, so it might not come as a surprise to you that I can do the same thing about the y-axis, so moment of inertia about the y-axis, and it also doesn't come as a surprise to you that I take the area integral and now I square x actually and dA, and then this is also in lengths to the power of 4. So same thing, just that now you're actually rotating about the y-axis. So that's actually important. So let's write that down. So this is the moment of inertia about y-axis. And I say it one more time for the risk of boring you, that this is about, right? It's not in the direction of the y-axis. Students often come to me and tell me like, hey, this is the moment of inertia in the y direction, but no, it's not. It's about the y-axis. It's not in the direction of something. And now, to keep no secrets from you and to tell you the full story, let me also tell you that you could also rotate about the pole. We will not do much about this, but for completeness, I'm going to add this formula here. But you can take the moment of inertia about the pole. So this would be about the z-axis. But because you're dealing with an area, or the potato chip, and not the entire potato, this is not a three-dimensional body. Because it's not a three-dimensional body, this would not be IZ, although a lot of people call it IZ, right? IZ. But it's actually better called JO, which is the polar moment of inertia. And now the question is, how do you calculate that? But the answer is already given in this picture, right? You have R here, you have Y here, and you have X here. And remember that from your basic trigonometry classes or geometry classes that R square is equal to X square plus Y square in this example. And therefore, you can actually say that your integral now needs to be x squared plus y squared and then dA. But because of this relationship here, because of that, you might as well calculate R directly. And you can do that by the actually it's not an integration anymore, by just summing up IX and IY. So nothing could be simpler. And that's why I think it's a waste of time for me to make you calculate the polar moment of inertia, because really all you have to be able is to calculate the moment of inertia about x and about y. But when you hear polar moment of inertia, this is the formula that you would use, and ultimately in practice you would end up using this. So now we have this defined for a general case here on this page, and that's great. What I want to do with you next is to actually classify and characterize this formula here, these Ix and Iy, for very common shapes. I want to do it for rectangulars, triangulars, for squares, circles, semicircle, and so on and so forth, so that you don't have to deal with these integration. Remember that ultimately for the centroid location, we also started with an integration formula first, but ultimately ended up with the summation here of a finite formula. So I want to do the same thing for you now and want to move from infinite integration to finite integration, and that's what we're going to do on the next page.